Hi everyone, welcome to the second session on the chapter of bending. Before talking about the new topics, as always, let me give you the review of a previous lecture. So in previous lecture, as a first session of bending, we defined what is pure bending. Okay, so as I told you, until the midterm, we are concerning the reactions one by one, and based on like a single force or moment, we'll try to obtain the stress strain distribution and deformation of the body, and we're gonna try to combine everything after midterm. Okay, so because this is a chapter about pure bending, we have to do the definition about pure bending. And in the example of weightlifter, we considered like a 1, 2, 3 sections of this bar, and found that only this section corresponds to pure bending, which is defined as m equal non-zero, and all other reaction becomes zero condition. Okay, so this is the definition of pure bending. After defining the pure bending, we discussed about some assumptions we have to make about the pure bending, which is based on the observation. So we made like a several assumptions that original cross-sectional plane remains planar, and this plane keeps 90 degree from neutral axis and etc. But of course we can mathematically prove those assumptions, but because we do not have enough knowledge about partial differential equation and advanced mechanics, we made like several assumptions, list of assumptions, and based on that assumptions, we try to construct geometrical, mathematical relationship, and based on that, we try to build up the relationship between curvature of radius and strain distribution. From strain distribution using Hooke's law, we obtained stress distribution. From stress distribution, we can make a connection to applied moment M. Okay, so if I give you the visual example, the radius of curvature of neutral plane, please say that remember that this law is defined for neutral plane, and and we denote this radius curvature as rho, and we considered like a neutral plane whose length preserves as original length, and we consider the compressive zone and tensile zone, which is above and below the neutral plane when m is positive sign. Okay, then from geometrical analysis, we were able to obtain strain as a function of y is given as minus y over rho, and which becomes minus y over c epsilon x maximum, where c is the largest distance from the neutral plane. And having obtained this linear relationship, we can also obtain the stress distribution in terms of y using the Young's modulus E. Okay, then from the force analysis, where the n must be zero, we found that neutral plane go through the centroid point by proving this guy. And then we discussed about the torque analysis. The infinitesimal torque on cross section must be same as applied moment m, and the out of this analysis, we found that m must be sigma x maximum divided by c multiplied by this this interesting integral, and we define this integral as area moment of inertia, and our textbook denoted this as I. And having defined I, we can obtain the relationship between m and I and c and maximum normal stress, because we know maximum normal stress in terms of applied moment and geometrical parameters c and I. If we plug this into our expression, we can obtain so-called flexure formula. Flexure formula tells us the distribution of sigma x in terms of y and in terms of geometrical parameter. After obtaining this flexure formula and make a connection up to this strain, which is y over rho equals to be epsilon x, we found the radius of curvature for nuclear plane can be written as m over ei. Like 1 over rho is given as m over ei. So, in the end, we were able to make a full connection, like deformation, strain, from stress using a material property, from stress to applied torque using mechanical equilibrium condition, right? So here is equilibrium condition. Here is Hooke's law. Here we use geometrical constraint and geometrical relationship, and this is typical like a overall structure of theoretical mechanics. Whether you do this elementary mechanics in second year of undergraduate, whether you do like a hardcore tensor analysis in graduate school, this is the basics. You use mechanical equilibrium equation, you use material property, you use so-called compatibility equation and geometrical condition to make a full connection between force and torque to deformation of the body. Okay, so you are going through these like I would say big picture view of theoretical mechanics, using simplest possible math. Okay, and regarding the full realistic analysis, I highly recommend you to take advanced mechanics course to get like a better sense on it. Okay, so with that, let me stop the review on the previous lecture, and we're gonna begin new topics in next video.